Okay, so basically, I just quick go over, okay? Make
Mr.
sure,
Pham,
yeah.
before you start, could I interrupt one more time and share my screen?
Oh, okay. Just a minute. I have to stop this.
I'm sorry.
Okay, now you can share.
And maybe, again, someone hopefully can just explain what I'm doing wrong here. So if I go here, you can see this is the answer I get with 1 over, where you end up with 2.5 and you're taking natural log, you end up, this is your RC here.
But the thing is, he said when you put 1 over, right?
Yes, sir.
So that's why you get a negative number. How come you get a positive?
I don't know.
Ah, that's quite different.
Okay. Then it must still be me. Okay, I'm sorry to interrupt.
No, Adam, this is the right one, okay? But when you do it 1 minus 3 over 5, that would be 0.4 instead of 2.5.
Okay, so
2.5, and that's where it's.
oh, I'm sorry.
Close bracket. Yeah, that's right. Close bracket.
Just 0.4.
Oh, yeah. Close bracket. And it's a negative.
Okay, now, all right.
Okay.
Now I see. Okay, thank you very much. I'm a little slow sometimes with the math. You can go on, sir. Sorry about that.
Okay, thank you. Okay, so multivibrator, okay, that is just a circuitry will be change the state between two digital level. That means on this type circuitry, the output only at a logic 0 or logic 1, or 0 volt or 5 volt, okay? And they get the three different type. Bistable, that means they're using the flip-flop. I will be go over quickly, okay, on the flip-flop. The second will be a stable. That means free running oscillator, okay? And also the last one monostable, or that will be a one shot. That will be given a single output pulse of a specific time length when it trigger from external source. So you can see quite different between three different. First one, they working just like flip-flop. Flip-flop, they will be get two output, okay? However, normally they get Q and not Q. But we deal with Q only, okay? We're not doing anything with not Q. So Q will be either equal 1 or equal 0, okay? That's what they call a bistable. Stable, basically, they just like, you get in a generator. You connect into the TTL logic, they just coming out with the square wave, whatever frequency. However, the logic will be 0 and 1, okay? And the monostable, they call it one shot. Basically, they generate just the pulses, okay? And that pulse will be changing for the frequency of a duty cycle of for the width of the one shot. And we already get to the capacitor. We already understand in the past we all learned capacitor, they will be charging and discharging. Okay. And when they charging, we already calculated tau equal R times C. That means time constant. Okay. Time constant. That means the time for the capacitor charge or discharge to 63.2% of the maximum value. And now we go in a little more detail to do the calculation. So if you want to calculate the voltage charging on the capacitor, then you use this formula. Delta VC equal E times 1 minus E power minus T over RC. And only two formulas we'll be using, okay? Delta VC, what did that mean? That means the changing in capacitor voltage over period of the time t. E, the voltage difference between the initial voltage on the capacitor and the total voltage that it is trying to reach. E just a natural law. T means the time capacitor allow to charging. And R will be resistance in ohm, C will be in Farad. Okay, on this example here, try to understand the example. Okay, that is the thing you're supposed to, okay, know. The thing is we are technicians, we're not involved much in any calculation. Okay, but if some basic, then we have to know. So in it, the first example, they say the capacitor initially discharged. That means VC equals 0. They want to know the voltage on the capacitor after 0.5 millisecond. Okay, if the switch move to the position 1. So basically you move the switch in here. That will be allow 5 volt. Then the current go through. See that? Okay, R and C. And the capacitor now will be start charging. Okay, so if you want to calculate the delta VC, after switch is moved from position 2 to 1, the voltage, okay, on the capacitor, that means you get delta VC equal E, okay, 1 minus only thing is try to understand what E, okay, E will be initial voltage, okay, the difference between initial voltage and the voltage capacitor try to reach. So now, initial voltage, they say discharge, so 0. And the voltage try to reach, that means if you keep live long time in this position, the maximum voltage on the capacitor will be 5 volt. So that the voltage try to reach 5 minus 0 equal 5. Then you substitute into the formula and you're able to do that calculation. Okay? So then the answer will be after 0.5 millisecond. Okay? They will be 3.27 volt. Okay? So now if I say let the capacitor full charge, so that what is the current flow through the resistor? If the capacitor is full charge, my question is what the current go
Zero current?
perfect
0.
0. The thing is both sides of the resistor you can get the same 5 volt. Yeah, that's perfect. Okay, and now if I asking you, I connect the switch into this way. So now capacitor will be the source, okay? And the current will be flowing the other way, this way. That means the capacitor now will be discharged to the right, okay? And if you take that long time, the voltage on the capacitor will be empty, okay? That's what I said, exactly your car battery. You turn on the headlight, you forget to turn it off. Next day, guarantee your battery will be empty.
Mr. Pham, I got a question on that 0. You said that was because it was 5 on both sides or what? What did you say on that?
Okay, that means you're talking about this position, right?
Yes.
Okay, so you get a full charge, then this time you get a 5 volt.
Okay, it's fully charged.
Yeah, fully charged. So if you get a 5 volt on this side, 5 volt on this side, current will be 0.
Okay.
Okay?
Yeah, got you. Zero, 5 minus 5 is 0.
Yeah, they get the same potential. No current can be free. Okay? Then the example number 2. Okay? They still capacitor initial discharge. The question is how long after switch is moved from position 2 to position 1. It takes for the capacitor to reach 3 volt. So the question here, they want to calculate the T. T equal RC time log 1 over 1 delta V E. Only thing in here, you need to identify what E equal. Initially discharge, that means 0 volt. Okay, and the voltage try to reach, that means you keep a position number 1, they keep charging, maximum will be 5. So will be 5 minus 0. And now you need to know what delta VC Okay. So they say the capacitor to reach 3 volt, they start 0 and they reach 3 volt. So delta VC equal 3. Okay, and you substitute into that formula, you're able to get the time. And the answer will be 0.431. So this is the last time I go over, okay? You get any question, anything, and try to ask it. The thing is when next week we coming back, then tech you will be get the quiz for tech you, okay? And we all, and now for the example 3. So they say the capacitor already charged to 1 volt. That means initially they get 1 volt. So the how long, okay, it move from position 2 to 1 will take for capacitor to reach 3 volt. So in here, same time, you need to identify what delta VC and what is the E. Delta VC, that means they start at the 1 volt already, and they try to reach 3. So basically, they only charging 3 minus 1, only 2 volt. And E, okay, E means the difference between the initial voltage and the voltage try to reach. In this case, try to reach still be 5 volt. However, initial is not 0. They be 1. So they will be 5 minus 1 equal 4 volt. Then you can substitute into the formula to calculate the time. Then you can get the answer will be 0.326 millisecond. Okay? Make sure you guys can really understand for this circuitry how to do calculation. Either the voltage charging or the time.
Mr. Payne, hold on. The one up top where you got delta VC equal 3, that's where it was 3 minus 0, right?
Let's see.
Where you got in red, where you have delta VC equal 3, that's where it was initially, I think that's number 2. It was initially discharged, so that would have been 0, and then trying to reach 3 volts, so then it would have been 3 minus 0, which is 3, correct?
Let's see. You're talking about example.
But you on in red, up top, you got delta VC equal 3.
Delta VC equal 3. That means
Initially, it was 0,
right.
and then you're trying to reach 3 volts. So
Exactly.
that's how you got 3 minus 0 is 3.
Right.
Okay, thank you.
That's example 2.
Yeah, okay.
Okay, on example 4, okay, initial they charge to 4.2. How long after switching move from position 2 to 3? Okay, that means they will be distant. You take for capacitor to drop to 1.5 volt. So the formula still calculate the time t. So we need to know what delta VC. Okay. Initially, they got 4.2. And now they will be discharged to 1.5. So the voltage capacitor discharging will be 4.2 minus 1.5. You get 2.7 volt. And E, okay, E means the voltage, the different voltage between the initial voltage and the voltage try to reach. You understand when you connect the switch to the ground for a long time, the voltage on the capacitor will be zero. That means they reach zero. And they initially they get 4.2. So A will be 4.2 minus zero. You get 4.2 volt.
So the initial one is 4.2, but you're trying to reach zero.
Right,
So it's 4.2 minus zero, which is 4.2.
right.
I'm just trying to get the wording together because you use the words initially and then the word that you're trying to reach.
Yeah. Initially, you have to know which one is initially. The thing on this example, they already telling you initially charged to 4.2.
Okay.
And now try to rate. If you connect that output to the ground, finally, they will be reach zero.
Okay. It's trying to reach zero.
Right. If they connect to 5 volt, that means try to reach will be 5 volt. Okay. And now another type, free running oscillator. Okay. First thing is they're using the IC74SC. SC, that means high speed CMOS. Okay. 14. So basically, they will be working the same like inverter 7404. Okay. For TTL logic. Only thing is the difference will be the voltage low or the voltage high. Okay. So if we already talked to you yesterday, and the input of this IC, okay, is low when they get 1.6 volt. Okay, 1.6 volt here. That's supposed to be low, and the output will be high. And normally for this SC, high speed CMOS, high, they supposed to be around 4 up to 5 volt. Okay. On the one you already know from 2 up to 5 volt, that's for TTL logic. Okay.
Hey, Mr.
Okay.
Fan, is this 1.6 and all this stuff, is this based on manufacturer or data sheet specs?
Right. Exactly.
Okay, thank you.
So, however, whenever you see HC14, then you can remember. The thing is the data here, they take from the data sheet of the IC. So if you get a 1.6 volt in here, they consider to be 0. And the output supposed to be 5 volt. Okay? And now, if you get the input, let's see how many volt here, 2.75. So if you get the input now stuck with a 2.75, okay, they consider to be a high input, then the output will be 0. That's only the difference between the TTL inverter 7404. Okay? And when you stack turn on, okay, turn on the power, the capacitor here will be shorted right away to the ground. So the voltage here will be 0. Okay? And if the input 0, output, they will be 5 volt. And now the current flowing this way. That's the current I. And they will be charging capacitor. Okay? When the capacitor reaches 2.75 volt, that means the logic high at the input, output will be low. Okay? So that will be showing you right here on the example here. Okay? So normally the output will be high right here at the beginning. Okay? 5 volt. You know why? The thing is you just turn it on. So the input will be 0. Output will be high. Okay? And the capacitor will be charging. Okay? Now, when they get high in here, okay, so the input high and the output will be going low. The thing is the capacitor will be discharged. So this stands for discharge.
So the capacitor will never fully charge nor discharge. It will hover between 2.75 and 1.67.
Okay.
Okay.
And this will be charging. Okay. Okay, so you know which one will be discharge and which one will be charging. And basically, a low threshold point here is 1.6. And this 2.75. Okay, so that's why when you connect power into the circuitry, automatically they given to you the square wave output, okay, and the level will be a 0 and 5 volt, logic 0, logic 1. And if you change the value of I and C, then you are able to change the period, okay, frequency of this signal. So we get one example number 5 here. So they said draw the waveform for the Smith trigger. So that's why we can draw right here. We already did it. Okay. And they want to calculate the time high, time low, and the duty cycle and frequency. If they given to you R equal 10K, C equal 0.022 microfarad. So basically the only one formula will be easy. T RC log 1 minus delta VC over E. So if they want to calculate the T high mean right here. That means the output high. So T high in here, and you need to know what is the value delta VC and what is the value of E. Okay, so now you can easy to recognize capacitor start right here, 1.6 volt, and they go up to here, 2.75 volt. So delta VC means the capacitor voltage charging, the difference between 2.75 and 1.6. Okay, and the delta, no, sorry,
That should be delta C.
yeah, delta VC. Okay, and E. E means the different voltage between the initial voltage and the voltage try to reach. You can see they start right here. Initial will be 1.6 and the voltage try to reach. That means they keep going. Then they go to the maximum will be a 5 volt. So they will be 5, 1.6.
Mr. Pham?
Yeah.
I think this is maybe a point of my confusion from last night. So this formula for T, we're just using RC times natural log times 1 minus delta VC over E, not 1 over 1 minus
No,
delta VC over E.
that over E.
It should be 1 over 1 minus delta VC over E.
So it still should be the same exact formula.
Yes.
Okay, that's, I think last night when we got to this step, we wrote it this way that he's writing it right now, and I didn't understand the change between the two.
Yeah, it should be 1 over all of that.
And when you use 1 over, that just gives you the same absolute value, but it makes it a positive number, not a negative.
Yeah.
Got it. Okay, thank you.
Okay, that is you calculate the T high. Any question for calculation T high?
Yeah, just go over one more time, Mr. Pham, that last E where you got E minus 1.6.
Okay, if you want to calculate the T high, then the formula will be RC 1 minus delta VC over E.
Mr.
Only,
Pham,
We already know R and C.
Mr. Pham, you got a question real quick. Go ahead, Mike.
Mr. Fan, this should be natural log
Yeah.
one,
LN.
1 over all of that. You're missing the 1 over that. That's why Adam was confused.
Oh. That,
Thank
that is, I think, it's not the LO. LOG, that's a different. LN.
No, but there's still the same formula. Your formula from the beginning is 1 over all of that. If you go back a couple of pages,
Okay. That one right here, right?
yes, 1 over.
Oh. I'm sorry.
After the 1, there's a slash. Yeah, I see what he's saying.
I am sorry. That's a typing wrong.
So is that supposed to be 1 over?
No.
It's supposed to be 1 minus.
Right.
Okay. So I guess he's saying that's supposed to be 1 over, Mike and Adam.
But then if it's 1 over that, then the number become a negative. Then there's all the answers are wrong.
Right. They cannot be 1 over. That's a formula. That's a typo. Yesterday, you're not telling me.
So, hey, Mr.
Okay,
Pham,
so
we might have to start all
then it's
over again.
just 1 minus.
Yeah, just a
So-
1 minus.
So, Mr. Fan, what you're saying is when the capacitor is charged, let's see. Because if you go up one more page, okay, that's the same formula there. So that's when the capacitor is charging and discharging. Okay, is that formula right or is that wrong as well?
No, wrong.
But if that's wrong, then the answer you get at example 2 would be a negative number. It's no longer positive.
It would be the same value, but it would be negative. It would be negative 0.431.
Hey, Mr. Pham, I hate to say this, but I really hate to say this, but I think you need to start over again because everybody's been getting that 1 over and they've been getting wrong answers. So now in their head, they got wrong information.
Okay, so let's
So
see.
you need to start over.
But
Yeah.
I guess, I mean, to me, the way I was understanding it was since it's the same absolute value either way, and the answer is in milliseconds, it's not going to be negative milliseconds. So you would just ignore the negative sign.
Mr. Smith, do you mean that
No, I
basically
need
Mr.
to-
Van have to go over the class again?
Not the whole class, only this
The-
part where we're
the-
doing this.
The last 2 class, right? The last
Start
2
over
classes.
at Tech 1. Start over at Tech 1.
Sorry, I want to.
No, only this part right here where we doing this charging and discharging, because I think a lot of students and myself included, and based on some of the questions we're hearing, not everybody's not understanding. And then that formula was wrong. So that kind of puts a double whammy on it.
Okay, I try to double check it.
Yeah, like Mike was saying, and like when I was sharing my screen earlier and trying to do the math in front of you, if you use 1 over 1 minus delta VC over E, your answer will be the same, but it will be a positive value instead of a negative value.
Okay, just a minute.
Yeah, I was going to get my answer off of Mike's and Adam's paper, but I don't know now.
That's dangerous stuff. No, but I think Michael was right. The way he explained it makes sense to me now.
Yeah.
Because again, if you do it just 1 minus delta VC over E, you will get a negative value, but it will be the same number, just a negative.
Yeah, 'cause when it's 1 over, it's like you're taking a reciprocal of all that stuff in the that's after that.
Right.
Yeah, just give me a few minutes.
Yeah, that formula is right actually. What the so the answers that he put up should be wrong.
Yeah, I have to correct that.
Right.
I think I got confused too, because there have been other sections where when we're doing the math and we come to the answer, there may be a negative sign, but we just ignore the negative sign and just go with the absolute value of the number. So I thought maybe that was what we,
That depends on you talking about the amplifier.
right.
The thing is, AC, you don't care about the sign. DC, they need the sign. AC, they cannot tell which one is positive, negative.
Negative just mean out of phase, right?
Right. Gee. Okay, let's see for 22.
But then if the answer is in a negative and the unit is millisecond, what's a negative millisecond?
That's the
Because time only goes in one direction, right? So are you going back in time?
It's supposed to be positive, the absolute value, but normally they have to be positive. You cannot calculate the time to get a negative time.
Right. Or we just invented time travel. So then it must be 1 over.
Okay.
You're gonna have to fix this on the web too, for the handout.
It's not 1 over. If you take that delta VC equal to E times that bracket, if you put it in term of T, then you will get that 1 minus delta V over E and not 1 over of that. So that formula is correct.
Just a minute. I try to see I can find it.
Man,
Mr.
this problem must be really hard.
Mr. Pham.
Yeah.
You want Mr. Hong Fan to run through some of the tests while you're checking this out?
What do you mean the get value?
No, Mr. Hong Fan, the other Mr. Fan to run through some of the DLab while you're checking this out.
Okay, now what I want you guys to do. You doing calculate this part for me. T high.
Can we do one more time the same example and find out some mistake in calculation?
That's what I said. Go ahead and calculate that T high for me.
Which one are you talking about?
I'm talking.
You mean I'm not fair or what?
What problem? What are you talking about? What are you doing?
I want to doing a calculation. Oh, okay. I see.
Next
I
page.
have to stop this guy. Okay. I want you to calculate the T high for this circuit.
Which circuit?
Can you share your screen?
Oh, sorry. Calculate T high, T low.
Are we using the same voltage for the
Same voltage.
sorry?
Yeah, the same voltage.
The same one, the 1.67
Yeah,
and
1.6, 2.75.
okay, thank you.
You're using the formula 1 over 1 minus delta V over E.
Can you say that again? We're using a formula 1 over 1 minus delta V
See,
over E.
D high. Okay. Equal RC log 1 over. Okay.
But I thought we decided the formula is incorrect. It should be not 1 over, just 1 minus delta V over E.
I'm just glad because I feel now that my question wasn't so stupid.
We're all in the same bag, Adam.
Okay, using this formula to see what you get. So you can see R times C, 150. Okay, and then 50 times 0.1. Okay, basically time. Ten power minus 6. Okay, time log 1 over 1 minus delta VC over E. So basically you can get Who get the answer?
And Mr. Pham, I don't want to be a bug, but you're just gonna have to go over this because I hate to be a pester about this.
That's what I given you the formula. I want you to do in calculation before I can decide to do anything else.
Okay,
So I want to know what the answer you can get. Who tell me what the answer?
okay, so you got 150 times 0.1 microfarads. Let me see.
How much is delta VC?
What you get?
How much is delta VC?
We already telling you delta VC, that will be T high. So that will be the difference between 2.75 and 1.6.
Okay, using your formula, Mr. Pham, the answer is 5.87 times 10 to the minus 6.
5.87
Yes.
T high, right?
Yeah. So 5.87 micro.
Okay. Now, can you do again one more time without 1 over?
Without 1 over, it will be minus 5.873 times 10 to the minus 6.
If you have a no 1 over, okay, that means you get a 1 delta VC over E.
Right.
What was E equal to?
Now, this is what I found, Mr. Pham, okay? The equation that we started out with, where delta V C over E is equal to 1 minus E to the power of minus T over RC, okay? And then when you factor that out in terms of T, what happened is you're missing a negative sign from the T. So T should be equal to minus RC natural log 1 minus delta VC over E.
Okay, let me calculate.
If you take the original equation, delta VC equal to E bracket 1 minus E minus T over RC. Note that minus T, if you factor it in term of T, you'll find that it will be minus RC. And that is why that will take care of the negative.
Hey, Mike, what did you have for the big E?
Big E, that's from previously when we did it. And that number is
E equal what? Something minus something.
for the high is 5 minus 1.67. So it's equal to 3.3 volt.
Okay.
You're just taking the same value from the example 5.
Okay. All right, thank you.
Delta VC we get that 2.75 minus 1.6, right?
Yes, 2.75 minus 1.67 equal to 1.08.
Will be a 1.15. You take a difference between 2.75.
And 1.6,
Let's see, 1 point
1.67 it says on the sheet.
let's see,
2.75
minus 1.6.
1.67 equal. That's equal to 1.08. Did somebody get that?
1.15.
No. 2.75 minus 1.6 is equal to 1.08.
How?
Did anybody get that?
I get 1.15.
No, 2.75 minus 1.67 is equal to 1.08.
Yeah, that's what I got.
Oh,
Yeah, I
1.6.
got that.
Okay. 1.6 đấy bạn. Okay, so 1.08 over E. E means
2.75.
2 point,
Oh, no, it's 3.33.
3.3.
Yeah, we're doing the high, so 3.33.
that means E means the initial. Okay, 2.75.
E is 5 minus 1.67.
Okay. That will be 5 minus 2.7 initial. 1.6, right?
1.67.
Okay, 1.67.
So that's equal to 3.33.
Mm-hmm.
3.33. Okay, let's see. 1.08 divided 3.33 equal. Okay. 0.324. 1 minus 0.324. And you get 0.6.
0.676, right, Mr. Pham?
676.
Yeah.
Okay, and 1 over.
Then you should get 1.479.
Okay. Let's see. 1 by 1.4. Okay, so basically you take a log of 1.479. Okay, and time 150. Okay, so
So then is the right answer 5.88 microseconds?
5.87 microsecond, yes.
Okay. All right, we agree on that. But you're saying if you take a negative of the RC natural log, it will replace the 1/over step and give you a positive value?
Yes. If you take the original formula and then you rearrange it, that's what it should be equal. It should be equal to minus RC natural log of 1 minus delta VC over E.
Got it. Okay.
Mike, what answer did you, so just in case, what answer did you get for this?
Same as Adams. 5.87 microsecond.
5 point what?
87 microsecond.
Okay.
And just for sake of argument, does it matter which way you do it, whether you use 1/over or negative RC natural log?
I'm not too sure, but somehow we gain the same answer.
Right. More than one way to skin a cat, I guess.
I guess so.
Okay, so we have to stop here. Next Tuesday will be get the correction. I have to look into that. The thing is, we're doing a calculation. And basically, we get a wrong one either.
I messed up the whole class.
Ooh, this is different too.
Right, that's what I said.
Adam, you party pooper?
Me and my big mouth.
No, that's good that you brought this up. So Mike, I'm going to depend on you. You and Adam, 5.87 microseconds, because I'm still trying to figure this out.
Right. Now, this is assuming that the
You're throwing a bug in it now. Go ahead, Mike. Go ahead.
this is assuming phi t is plus 2.75 and phi t minus is 1.67.
Right.
Okay, here's what I got. I got E.
On this Mr. Pham's worksheet, it doesn't show that. So I'm just thinking.
Okay, but here's what I'm doing. E, the big E is equal to 5 minus 1.6, which is equal to 3.3.
That is for the high you're working on, right?
Okay,
Well,
I'm telling you guys, this is answer will be 10.12, but not the calculation. That is a run P5.
Okay.
But supposed to be calculation supposed to be the same. Only different is maybe 7414 in the P5, the voltage level may be different.
Right. So if it's different, then all the answer would be different.
Right. Okay. I need to look into the book. I don't know where my get book.
hey, Mr. Pham and Mike, if we could, and Mr. Pham, maybe you could do this. If you could just write on the screen on your notepad what big E is and what delta VC is, and then we can just play around with it on our own until we see you next time. Because I want to make sure that we're all on the same page, consistent.
Okay, the value should for delta V, C, or E will be the same thing. Okay, now I try to stop there on that one. Okay. And I try to See on this graph. Okay, so basically for any problem here, okay,
I think it's the next page down.
that okay. Okay, that is the formula here. Okay, I'm not sure. When we get another formula right here, that's a different. However, what I say on the example 1, 2, 3, you already know what the delta VC
Okay.
and what E we already given to you. That
Well-
cannot be wrong.
Okay, so the formula for T right there, is that correct?
No, that's what I said. I have to check.
Right. And then for the delta VC and E is actually on the next page down, Mr. Pham. No, down, not up, down.
The other way.
Keep going. Oh, right there. Okay.
Okay, right now we
One
calculate the
more page.
time.
One more
Hey,
page.
Mr. Pham, expand your page so we can see the end. No. Stay there, stay there.
No. Keep going down. Keep going down. One more page, Mr. Pham. No. The other way. Okay, those are the data sheet value that you get for the VT on the high and VT when it's on the low.
Right,
So those do not change.
cannot change.
Right. So those are the data sheets. So therefore, your deltas VC and E is worked out from those number respective to your 5 and your 0 volts.
Exactly.
And then you use the same thing when Mr. Pham had that other problem, you're using those same numbers for it.
What I say is, this one you can say delta VC and also E. Nothing change on that. They already given you the VT plus 275, VT minus 1.67. Only thing I'm talking about the formula. I need to look at that to correct it.
Hey, can I see that page above that, please?
This one,
Yeah, but part of it's cut off where you wrote it. I want to see the part where you were writing. Yeah, there you go. All right, thank you.
you're welcome. Okay, so I will be set up specially just for capacitor charge and discharge. Okay. And now another one, monostable. Let me the one shot. They're using the IC 74121 or 123. So you can say for this circuitry, okay, and when you connect the external R and C right here, whenever you apply the trigger, this is the trigger right here, then the output you can get a pulse coming, okay, and the period or the TW, the Y of the pulse, depend on I and C, okay. Every time they trigger, positive trigger right here, then it's going up, then how long they can going down, depending on I and C, okay. Here they say these pulls are ignored by the one shot, okay. So the first one here, you get the 1, but this is longer than the time of the pause. So that's why they ignore that one. Okay. And non-trigger, that also same different type of the circuitry. Okay. They trigger, they get a pause coming out. Okay. And when the trigger, they get another one. And you can RNC. That means you can the wait the time, the width of the pause you want it. Okay. And on that one, they say re-trigger. That means when you apply the pause here, okay, and they go and they can trigger another one here, you get another TW here. That's a just re-trigger right here. They're setting the pause width TW equal 0.7 times C. So if you want the width of the pause, you can select I and C. Okay, I and C just external.
Mr. Pham, I don't quite understand between your two different slides. On the first one, if you go up one more page. No, you passed it. Right here. Say, on the lower one, it say these pulses are ignored by one shot. Okay, because your width is wider than the trigger.
Okay, now you can see on that one, when they trigger it, the width here, right?
Right.
And
Yes.
that depends on I and C.
Right.
Okay. Then you get a trigger second time, they give another one.
Right. I follow that.
Okay, now on this one, when you trigger here, then you trigger here, right?
Yeah.
So basically, this first trigger here, they get a TW longer than the time you trigger right here.
Right. Correct. So I follow that.
Ignore it. They don't care that part.
I follow that. But then on your next page, you're talking about re-trigger, which is within the same amount. Oh, okay. It is right at the end there. Is that why? I mean, if that is still within the time, shouldn't that be ignored?
Let's see. On that one, A, B, what they talking about B? Nothing.
What makes one retriggerable and one non-retriggerable?
Right. This is a re-trigger.
Right, but then that when it re-trigger is still within the TW.
That means they can re-trigger for this quantity W, right?
Right, but it has to be, doesn't it has to be after TW? If it's within TW, shouldn't it ignore it?
If you can see this from here to here, okay, that's a one portion, right?
Correct.
Okay, so basically they're supposed to be from here to here, right?
I cannot see where you're pointing.
No, what I said exactly this one.
Mr. Pham, you need to use your pointer.
Okay, I see it now. Okay, from there to there is one trigger, the TW.
That's right here,
Yes.
okay? However, they're supposed to going down, right?
Mm-hmm.
Go. However, they say re-trigger. That means they trigger again, and they keep moving to the next one.
Right, but then that re-trigger is before the end of TW. Shouldn't that be ignored?
Now the ignore in here, okay, right here, right?
Right.
Okay, you can see the pause going out this way, right?
Right.
Up to here, they can stop.
Mm-hmm.
So they say no matter what pause coming in here will be ignored.
Right.
Okay, now on this one here, you can see the pulse supposed to be, okay, from here to here.
To there, and then the
Here.
trigger. Right.
Okay, then they go down, right?
Correct.
However, in here you get another pulse here. Therefore, the circuit re-trigger.
Right, but the pulse is before the end of it. Shouldn't that be ignored?
Yeah, it looks like the trigger pulse should be a hair further to the right to allow for when
They keep going.
Right.
when TW falls to low, the trigger pulse should be at a high to re-trigger another full.
Exactly. They re-trigger, they give you another one.
I think maybe the way the diagram's drawn is just a little bit deceptive. That second trigger pulse should be slightly more to the right.
When the trigger go from low to high, shouldn't that be at where TW ends?
Unless the trigger pulse is high when TW ends, and then it will just continue another TW.
Okay, now you can see it right here. If this one without this pulse, they will go up here.
If that second trigger pulse was half of its own width to the right.
No, I'm talking about on this one here.
And you use the pointer.
Re-trigger. Then they can go up to here. Right?
Yes.
And they go down. See that? Can you follow that?
Yes.
Without that pulse. Then they go exactly like the first one here. You don't have a dead. However, this is a 74123. That's a re-trigger IC. Then they re-trigger right here. So now they start from here and count another TW. So they keep going. They not stop it.
But if it's re-trigger before the end of the first TW, should
Before the end. Before the end here, right?
well, the first trigger, okay. So
Okay.
it ends where you draw the red line. They say if there was no second trigger.
I can tell you on this one here. Okay. Now, if they trigger, okay, then they go up to here. If I get the re-trigger right here.
Right, that would be ignored.
No, if the re-trigger, that means the IC 123. And this is the IC 121. So if you're using a 123, then when you get another port, then they start from here, they keep going.
Oh, so you're telling us the IC here is different to the IC on the page.
Right, that's what I said right here.
Oh, I was missing that too. Okay.
Okay, now that explains it. So
that's what makes one non-retriggerable, but one retriggerable.
Right.
Okay.
That explains it.
Okay.
Thank you.
Yeah, thank you. Sorry.
No problem. Okay, I will go over this one, and we will be talking about next meeting. This is what they call a 555Timer. Okay, see how they work it. The dark part right here, inside the IC. Okay, this will be outside pin number. But I try to explain to see what's going on inside and what do we need to know. First thing you know, this IC here. that will be comparator. Okay, how they work? They will be compared between the input positive and the input negative. If positive higher than negative, output here logic 1. Okay, they're not using saturation. That's a logic. If a negative input higher than positive, output will be low. And this also exactly the same thing. Okay, and this one, RS flip-flop. Okay, this is the RS flip-flop. We have to go back to the RS flip-flop. And if you get a high in R or high in S, what is the Q? Okay, and this one here, inverter. If you get a 1 input out here, output will be low. You get a 0 here, output will be high. Okay, and finally inside here, you get a NPN transistor. Okay, so basically, if a logical 1 in here, turn on the transistor. When the transistor be turned on, basically they will be connecting 7 here to the ground. Okay, if the logic at the output here is 0, that means the Q1 will be off. They open from pin 7 to the ground. Okay, finally, I can ask you, if you get a 15 volt in here, can you tell me what the voltage here?
7.5.
Okay, now 15 times 10, right? Divide 50, 5, 5, 5. Voltage divider. You see that? 1 R to 3 R to the round. So if you want the voltage in here, you take 15 times 5 plus 5 means 10. Divide total. 5, 5, 5 means 50. Okay, now what the voltage at this point right here?
Bifold.
15 times 5, right? Divide 50. So basically, if you know the VCC right here, you're able to tell what the voltage here and what is the voltage here. Okay? So when you apply into the circuitry, you're able to know. You see that? This is the one they make the connection. And they given you VCC here. Okay? And also they can calculate the TW at the output here. So basically depending on, you can see you get a R1 here, okay, you get a C1 here, okay, then you know how to calculation here, a little more detail here. They given you that one. I make sure you read, you understand. Whatever inside the blue one, okay, inside here. That means inside the IC. This is you want to connect it outside R1, okay, and C1. Then you can see how they working. That means they will be charging, okay, or what else. Okay, so try to read it, okay. For example, on this one here, okay, if you get the VCC here, okay, then you know what the voltage at the pin number 5 and what is the voltage at the pin number 2, okay, number 5, number 2. And also you can see when you get the power here, okay, then the current will be go into here, okay, then they go into R1, R2, then they charging capacitor, okay. So when the capacitor go up to a certain voltage, and now the transistor here will be turned it on. They connect pin 7 to the ground. So that means connect it to the ground. So the capacitor now will be discharged. So let's see, this is what they want output right here. Basically, just a pulse coming out. One. That's why they call it one shot. And period will be T high, T equal T high plus T low. T high equal T low equal, and a duty cycle. That's a formula to given to you. Okay, so basically a lot of detail on this thing here. Okay, you can see that the current flow for charging, and this is the current flow for discharging. And that's why you can get this output right here. And they keep charging, they keep discharging. And if you connect it out oscilloscope to the output, you can see square wave. Okay, if you can R and can C, that's what you can see the different frequency, the different pulse width. Okay, and also they will be telling you in here the VC. And when we're doing a simulation, okay, there's a simulation, then you can see exactly what we're doing. Okay, so now I believe the formula will be RC log 1 over. You see that? Delta VC over E. So that means only thing is telling I can get the wrong, okay, the wrong calculation with the formula at the beginning. I think that will be wrong.
Which one you think will be right?
This one. 1 over.
1 over, okay.
Where I put the one, not 1 over.
It's a couple pages down.
Hey, for you guys to know, just in case some of you were saying
Keep going.
some of you were saying 5 minus 1.6 is 3.3, it's actually 3.4.
Well, the actual value on the sheet is 1.67, not 1.6.
Okay, I see what you're saying.
I saw the one without 1 over. Where is it?
Oh, you had actually handwritten that one. It wasn't on the. It wasn't on the
handout.
on the handout. You had actually just hand wrote it in.
Oh, okay. Okay. That makes sense to me. Okay. I will be,
It was on this page that you had handwritten it.
okay. Thank you. So the formula that are inside the handout is correct. Okay. 1 over. Okay. So next Tuesday. We,
Okay, Adam, and so that's 3.33 then.
Right.
Okay. I will be double check for the answer of the example. You
And
mentioned,
Mr. Pham, this formula right here, that where you on this page where it says number 2 capacitor charge discharge, these are the right formulas, correct?
right. On the formula here will be right. Only thing is, he said I wrote it wrong when I do calculation. That's why I can find without 1 over. I couldn't find anywhere here.
Right. And that, yeah, that was what confused me, was that it just, it looked inconsistent and I wasn't sure which one we were supposed to use.
Okay.
But the formulas are correct.
Yeah. Every correct formula in this handout correct.
All right, okay, thank you.
I wrote it wrong.
Hey, we figured it out and that's all that matters.
That's it.
Had a healthy debate.
The thing is, after this chapter, you will be go into the next one, ADDA converter. That's a very short on the handout on the lecture. The thing, everything just inside the IC, and we not go into the inside of that IC. That's a designer. Only thing we deal with for A to D converter. That means you get an analog coming in, binary coming out. How that IC working. Then you can get the IC-DA converter, digital input and the analog output. Okay? That's a very short, not a long, like a multivibrator. Here we go more thing. Then that will be only thing we try to deal with the D lab. A lot of students still get a problem. I given you almost everything. And I want you to coding your program and to still get a more mistake. I say, okay, this is a function here. They get a declaration. Then you must be get the definition. And what inside the definition, I already given to you. That just try to teach you to deal with the function. After you get through that step, then now we can go more detail. You have to make your function definition. We get 2 left for memory. Most of that will be using function. Like you say, I want to write address to the memory. How many things will be inside that function definition? You have to write address, or you have to do whatever. Address will become into the memory. And if I want to say write data to the memory, then you have to know how data can come in to the data of the memory. That means including write data to memory. We don't want to write step by step for each test. That takes too long and hard to follow it. You can do a second one for IC 2114 more easier if you understand. Take about 1 hour coding, and that will be done. I said this is a very important thing for the technician. If you not quite understand, you just in Zoom with me. I will explain to you. Okay? So we can get a tomorrow day. Okay, go over the final test. And will be stopped and your guy will be returned on Monday. And after the fourth week of the summer, you still get Tuesday meeting. Take one get Monday and Wednesday. However, after fourth week, okay, the second week of the summer, I take only 2 days. Monday for take one. That means AC only. Tuesday for take two. And Mr. Tai will take the guy on the left phone for 2 circuit board, AC1 and AC2 will be on Wednesday and Thursday. Okay? So we don't have a much thing. If we can get AC done quick, then I will be take the guy in the basic RF radio frequency. Okay? That means how the signal transmitted over the air and how the signal will be received. Okay, so any question?
Thank you, Mr. Pham. Sorry for throwing a monkey wrench in your lecture there.
That's okay. That's good. The thing is, we work together. Okay, I'm not a master. You
That's
can
right. We're a team, Mr. Pham. We're a team.
you say in the program it's the first time in my over 35 years running this program. I get a one master, Mr. Richard.
Yeah.
Yeah, the thing he get a MS double E. That means I get only BS of double E. Okay, cannot compare.
Oh, you guys are like Yoda and Obi-Wan Kenobi.
But the thing is, he have a lot in the program, and I think he don't need that certificate anyway. But I saw him be in the program every time.
I think he said he wants to teach a program himself, so he's learning from you on how to teach.
How to
You have stuff to teach him too. Don't worry.
you understand the teaching is the art. Okay, that means sometimes you know, but you cannot teach.
I know the feeling.
The thing is, the student not understand what you're talking about.
It's easier to do something than it is to teach someone else how to do it.
The thing
But
is,
you have to come up with ways of showing somebody if they don't know something.
I've been teaching from I get 20-year-old teaching for the 12th grade math and the physics in my country. Okay, And so far, okay, you can see we get a different instructor, but how many instructor can talk, can teach, okay? Teaching, that really like a singer, they can sing and song. However, everyone want know how to sing it, but who can be a singer? No, that basically your voice, okay?
Adam and Mike, they can sing.
Oh, please. Hey, Mr. Pham, if you can teach me this stuff, you could teach a monkey this stuff.
All right, thank you, Mr. Pham.
Thank you very much.
No problem, okay?
Bye-bye.
We'll see you guys. Bye-bye. Good night.
Night.